Welcome everybody to today's session of discrete optimization talks. First, Jorge is giving his talk. Jorge Sefair is an assistant professor of industrial engineering in the School of Computing and Augmented Intelligence at Arizona State University, where he is also a senior global future scientist at the Global Institute of Sustainability and Innovation. Dr. Sefair is also affiliate faculty at the Simon Levin Mathematical Computational and Modeling Sciences Center, the Center for Biodiversity Outcomes, and the Center for Spatial Reasoning and Policy Analytics. In other words, he is the center of all of these centers. Dr. Sefair holds a PhD from the University of Florida, no preferential treatment given, and he has a master's and a bachelor's degree and various degrees basically from the Universidad de los Andes from Colombia. I butchered that. So his research interests include network optimization, multi-stage optimization, and of course, integer programming. He's motivated by applications of operations research, environmental planning, and all the other centers that he's involved in. And so I will just finish it off with the fact that he's been funded by many different agencies, and most recently, I guess he's been awarded an NSF Career Award from Operations Engineering, which we are very happy for him. So thank you very much, Jorge, for joining us today. It's all yours.
All right, so thank you very much for the invitation. I'm going to present this work, which is a joint work with Ankan Mitra, my PhD student, and former master students, Vishal Surendran. And I really like this project because it's a nice continuation of a master's thesis that evolved into a PhD chapter, and now it's going to be a paper, hopefully soon. So the title is Continuous Location Models in the Presence of Obstacles, an application to wireless sensors networks. And that's kind of a teaser because I know the name of this series, so I added the continuous location. But to be able to do what I'm going to show you, you need a lot of tricks from discrete optimization. So that's kind of the connection with the series. So let me start with the problem motivation. Wireless sensor networks are basically a group of sensors that are located in the space, and their purpose is to collect physical or environmental information. So you put sensors out there, and then you try to gather information remotely. The sensors can communicate between each other. They do it wirelessly. And then there is this sense of nearby sensor that guarantees that two sensors can talk to each other. So we will need to talk about connectivity and in which cases two sensors can communicate, or in which case sensors can communicate between each other. There's also a central sensor, or we will call it base node, that collects all the network data. I'm assuming in this case that there is only one, but they can be multiple. And if you look at the picture on the right, that's the blue sensor that's gathering information from the network. That network on the right is not fully connected. The red arcs are connections between sensors already deployed. And then you see that there are disconnected clusters of sensors that you would like to connect and gather more information from the network. So the sense of connectivity is that sensors must be within range to transmit data. So we will have to impose some distance constraints. Some of the already deployed sensors, they already talk to each other. So we will use that as a fact. And then also a sensor is connected if there is a transmission path to the base node. So if I want to assess the connectivity of this network, I will count the number of the green dots that are connected to the base node, which means I will count how many have a path between them and the blue node. Now, some challenges here. What I would like to do, what we like to do in this case, is to place something that's called relay nodes. So those are extra sensors that are larger. They have larger transmissions range, but they cannot sense. So I will use them only to transmit information, and I will use them to improve the connectivity of the network. Another challenge is that I have a limited number of those sensors to deploy. We will call that a budget. So you have only, let's say, K sensors to deploy. And also in the second part, I will show you the implications of physical obstacles, because they limit the deployment area. You don't want to place a sensor inside an object or inside a structure. And also they disrupt the line of sight connectivity. So I will go into the details, the mathematical details of what I mean by line of sight connectivity. Basically is that the sensors need to see each other, or the line in between them must be uninterrupted to be able to communicate. So obstacles will create that problem, that they disrupt the connectivity. Now, applications of these, there are some applications in the smart precision agriculture. So you want to sense the soil conditions, the humidity, the acidity, or many conditions of your field. So you deploy sensors, gather information, and then depending on what the sensors tell you, you deploy some measures, you water, you irrigate, you do something in the field to improve the conditions of the crops. And also smart cities, you want to check pollutants, you want to check environmental conditions. So you deploy your sensors, gather that information, and based on what you read from the sensors, you implement some strategies. Probably you control traffic, or you do something to reduce the exposure to pollutants. There's also applications in area surveillance and also remote fire detection. So that's kind of what the motivation of this problem is. Now, problem definition. So the first one I'm going to talk about is called the relay node placement problem. That problem exists. The definition is that you have a set of existing sensors already in the field and the base node, and you need to find the best location of K relay nodes to maximize the network connectivity. In other words, to maximize the number of sensors that you can reach out, or that they are gathering or sending information to the base node. And the second problem I will talk about today is an extension of that one, where you just add obstacles, and we're going to assume that those obstacles are polygon shapes. So as you can see in the bottom right figure, so those are going to be the challenge because they disrupt the connectivity or the communication. So you need to kind of go around the objects, and you cannot place a relay on top of the object. That's not allowed. I'm assuming objects are solid, but most of what we will show you, if the objects are not solid, or just you can send information through the object, that you just don't impose some constraints that I will show you. Now, I'll show you 4 geometrical insights that we will need for the mathematical program later. The first one is the concept of connectivity. So we will need to enforce some distance constraints. So the first one is the distance between 2 relays. I'm going to use X with superscript R to denote the location of the relays. So the first one is saying that for 2 relays to be connected or to transmit information, they need to be at a distance of no more than delta. The same happens between relays and sensors. The distance should be no more than beta. And I'm assuming here that the range of connectivity of the sensor is the most restrictive. So beta is less than delta. And also sensors already deployed, they communicate if the distance between them is less than or equal to beta. So in the picture I'm showing you below, you have 3 sensors that are connected, and they do it through 2 relays. So the first sensor is talking to this first relay in blue. That relay is talking to the second relay in blue, and then that second relay can talk to the other 2 sensors in green. So this part is fully connected given the presence of those 2 relays. Now, when there is objects in the field and the objects are solid, then the right picture is showing you 2 possible or candidate locations for 2 relays. But then if they talk to each other, then the line of sight is disrupted. So I cannot really let them talk because that's not possible given the object that is in between. So when we talk about line of sight, what I would do is take the locations of the relays that are communicating to each other and guarantee that the line in between them is not overlapping with any object. So in that case, that should be saying, okay, they might be within distance, but because of the object, they cannot talk to each other. So I will impose that through constraints. The second thing I will do is we created a Euclidean approximation to the Euclidean norm. As you will be guessing from the previous slide, I will need to use Euclidean norms a lot. So in this case, what we did is approximate the Euclidean norm using an outer approximation. So you will be thinking, yeah, this could be solved with conic optimization, but you will see, or I will show you later, I don't have the numerical examples here, but they don't scale. When I use second order conic programming for these, those models don't scale. I cannot solve the large instances as large as we're solving with this. So what we do is that we sample, so here in the right picture, I'm showing you just a very simplified example where you have a sample of unit vectors. In that case, those are the U vectors. I have 8 distributed across the circle. And then all the vectors at a distance of less than or equal to 1 in that example are the blue ones from that center point. Now, what I would do is I will create an approximation where I use the dot product between X or any vector there, dot the unit vectors, and that is less than or equal to 1 in the example or R in general, and that will give you the green shape. So the green shape is not an approximation, is admitting more vectors than what it should. But I can just fix that by adding more unit vectors. So I just have a outer approximation that tells me or helps me approximate that distance requirement using linear constraints, but I need a sample of the U vectors. So I need to have unit vectors at the beginning, and I can refine that on the go. I will show you that in the algorithm. And that's what I'm saying here, that the outer approximation converges to the real set when you have impose the Euclidean constraint, the Euclidean norm, as the number of unit vectors increases. Another thing I need to do is to model how do you enforce that the relays are not located inside the objects. So what we're going to do there is we're going to break up the object into cones. So if you look at this object on the right picture, all the possible or candidate points inside the obstacle are delta p, and then I'm assuming that I have the vertices of that object. I'm going to call that v of delta of omega p. In this case, I have 8 vertices, and I assume that I have an interior point that has line of sight with any of the vertex or every single vertex. And that's, you can find that point, and if you cannot find it, then you can just break that object into several sub objects and then just have more objects. But that's always possible to find that vantage point V0. And then the constraint I would like to impose is this one over here, which is that the location of the relay is not inside that object. And the way I'm going to do that is I'm going to say that the location of that object is in one of those cones, but outside the object. And the way I do that is I represent that location as the conic combination starting with vertex at V0, and then a conic combination between those vectors, vertex minus the center point. And I use SOS constraints to guarantee that only 2 consecutive vertices are selected. And then I impose this constraint that says that the sum of the alphas is greater than or equal to 1, which guarantees that they're in the cone, but outside the object. So for instance, in this example, I'm showing you where you have XR right there in red, I'm imposing a constraint that says that the relay has to be in cone 1, but then it has to be outside the purple area. And I can do that easily by controlling the weights, the continuous weights I'm using for the conic combination. So we call these ones push away constraints, because they take the location of the relay and push it away the cone for each object. Second thing I need to be careful about is the possible hiding or blind spots when you try to communicate with a sensor that is close to an object. So if you look at these sensors on the rightmost picture 1 and 3, they're located very close to the object, but if I do possible locations for the relays would be inside the circle and outside the object. So I impose just distance constraints and push away constraints, and I can get the green area. And that works very easily for 1 and 3. But for 2, I have the problem that if I impose the constraint that you have to be inside the circle and outside the object, I have these blind spots in white where you cannot place a relay because there is no line of sight with the sensor, which is in this case point X8. So I'll do that by simply creating hyperplanes that are, in this case, I have 3 hyperplanes from the sensor location. The sensor is already deployed, so I know that location. And then it's supported by this corner of the object. I have my first hyperplane here. The second hyperplane is a facet of the object. And the third hyperplane is is connecting the center of the location of the sensor. And this is supported by this vertex of the object. So basically this set, what it's saying is, if that relay, if a possible relay talks to that sensor, which we will use WSK for that, then the first constraint is saying, okay, they must be inside the circle. The relay must be inside the circle. It must be inside the communication area of the sensor. And it's also going to be below, in this case, one of the hyperplanes. So you pick the hyperplane that you want, but it has to be inside the circle, outside the object, and also below one of those hyperplanes. So this constraint over here is telling you, hey, you have to pick one hyperplane, and then the constraints for the other hyperplanes will be relaxed, and the constraint for the hyperplane you're choosing is going to be imposed. So you just remove those blind spots that you don't want. Another observation is or geometrical observation is the connectivity between relays. So this is the line of sight that I was talking about. So here what we basically say is that if there are two relays that are located within range and they talk to each other, I will need to check that there is the line between them is not overlapping with any object. And what I would do is I will create that line as a convex combination of those locations for those vertices, and I will apply just push away constraints from that object to every point in that line. So as you might be guessing, that creates this problem. If you see at the mathematical formulation, you'll have the product between the lambda, which I don't know, and the location of the relay, which I don't know, and that's continuous. So that's a problem that I'm gonna solve in the solution algorithm, but technically you can do it that way. You just create the line and then you just apply the same concept of the push away constraints from this object to every point in that line. So you just try to push the whole line away from the object, so you don't have any connectivity issues. Now, if the object is not solid, you just don't impose this constraint for that pair of relays related to that object. So you just let it be. Now, for the SOS formulation, SOS2 formulation, we're using the results from Bielma and Menhauser in 2011, and is the logarithmic formulation for the SOS2, and that helps us drastically reduce the number of binary variables that you use in the model. So in this case, I have this simplified example with 4 cones, and I have these potential the coefficients for each of the vertices, and then for each cone, I have in this case a binary code using only 2 binaries, gamma 1 and gamma 2, and depending the values of those binary variables, I just turn off or let be positive the appropriate coefficients. So for instance, when gamma 1 and gamma 2 are equal to 0, then lambda alpha 4, alpha 5, and alpha 3 are going to be equal to 0. And then the only ones that are going to survive are alpha 2, alpha 1, and alpha 2, because those are the ones that I can use to represent that you are in cone 1. So we use that trick to keep the number of binaries at the minimum, because as you might be guessing, if I do that conic thing and break up the object into cones, and I have a complex object, and you will have just a ton of binary variables. Now, jumping into the mathematical formulation, given those observations. So here, what I want you to pay attention to is the W variables. Those are connectivity binary variables representing connectivity between sensor and relay. The Z variables are connectivity between relays. QS is 1 if the sensor is connected, and Fij is a flow continuous variable between nodes or between sensors. I use those flow variables because I'm going to use a flow version of the connectivity constraints. In this case, I'll show you that later. Objective function is to maximize number of sensors that are connected. Communication range is just our dot product trick to approximate the distance between relay and sensors and between relays. Those are linear. And then the connectivity or flow version of connectivity is that the base node is going to offer the summation of Q amount of flow. Q is binary, or you can relax it, but it's between 0 and 1. And you can assume it's binary for now. And then that amount of flow is going to be distributed in the network. And then for each of the sensors, if they are connected, then they demand 1 unit of flow from the network. And that should be provided either by flow through relays or by sensors. And then the relays are going to be acting as transshipped nodes. And then, of course, if there is flow between sensor relay or between relays, then you need to activate the connectivity. So you need to turn on those binaries that reflect that they are talking to each other. The last constraint here is just I have a big box, a big rectangle, just to limit the number of the locations where the relays can be placed. And then variable type constraints, continuous location for the relays, and then also binaries reflecting connectivity, and then the binary reflecting that you connect a relay, a sensor or not, that you can relax that one and there's no problem. And then the flow connectivity is continuous. Now, of course, the other constraints given the geometrical interpretation I gave you, of course, the relays need to be outside the objects. That's the first one, obstacle avoidance. The relays need to be in the areas that are not subject to blind spots. So I should avoid blind spots for those objects. So I can pre-calculate which objects are critical and which sensor object pairs are key, and I need to impose those constraints. And also line of sight, when I have 2 relays and they communicate to each other, I need to be sure that the line between them is outside the object. That's the last set. And I have an asterisk here because I haven't solved the problem of that product of continuous variables. This is how we solve these. We solve it using a branch and cut strategy. So we let one branch and bound tree go. And then what we do is we get an integer solution. Then what we do is check distances. So we check the distance between sensors and relays between relays. And I check if there is any violation. Any violation means that the range of communication is or they are outside the circle. And then because I have a sample of U vectors, of unit vectors, likely I will have some violations. So if you find one violation, what you do is just construct a new U vector in that direction, and then just add it, impose a constraint, impose a cut, and keep going. So I can go as picky, I can be as picky as I want with the approximation quality. So you can just impose a limit on the number of U vectors that you accept, or you can go and have a very accurate approximation of the Euclidean norm. But that, of course, would require a ton of U vectors. Second thing we do in the branch and cut is check for violation of the relay connectivity or the line of sight. And then what we do is we are going to sample points in between that line when two relays communicate and they overlap with an object that is solid. So this is the technical part. Here's more in a schematic way. I just have, in this example, I have two relays located. I know that the line overlaps with the object, and I will do a sample of points in that line. In this case, I'm picking on this point with coefficients 0.8 at 0.2, and I impose a push away constraint for that point, and then I get a solution possibly like the one I'm showing in the middle. And then I can keep imposing push away constraints for the objects until I get something like this in the rightmost picture. Now, there is still a possibility that there is an overlap. So again, you guys, the sampling, the number of points you sample in that line gives you the quality, or gives you or you can be as picky as you want with that number of points and then get the quality that you want, or you might overlap a little bit. So if you move this line and then you try to make it or draw it on top of the object without touching any of the blue dots, you can do it. And that could be just reflecting that the waves from connectivity from the sensor signal are not straight lines, so they're kind of wavy. So that's okay that there is just a little corner that overlaps with the sensor. But if you are bothered by that, then you just impose more points. Some enhancements. So of course, the logarithmic trick helps a lot reducing the number of binaries. So I'll show you a sample of violent inequalities we use, and I will show you some other algorithmic tricks that we use to solve large instances of this problem. And then the network size reduction technique is something we're working on, and it's very promising. I'll show you the ideas that we have so far. So violent inequalities, so simple ones. If a sensor is connected to the base node and sensor J is connected to the sensor I, so then J is also connected to the base node. So I can impose that. We found violations of that in the linear relaxations. So you can just quickly break that up. If two sensors are too far from each other, then they cannot be connected to the same relay. So that's also helpful to impose. I can impose an upper bound on the maximum number of sensors that can be connected to a relay. So I can just pre-calculate and find that maximum number of sensors that can enclose in a circle of radius 2 beta, and then impose that constraint. And also we create an auxiliary graph where we have an H if the distance between two sensors is less than or equal to 2 beta. And then we do an independent set, any independent set. It doesn't need to be maximal independent set or maximum. And then we impose that constraint that says that, or that cut, that, or that inequality that says that you can connect at most one of those with a one relay. You can connect at most one sensor in that independent set, because they're by definition they are far from each other. Now we also impose symmetry breaking constraints. The sensors, I'm assuming they're identical, so we just impose an ordering in one of the coordinates. In this case, we pick on the y coordinates. So the y coordinate need to be non-decreasing. And then also we impose convex Hall constraints that only works for the problem without obstacles, and that's that the location of the relay needs to be in the convex Hall of the sensors. That helps also reducing possible locations for the relays. But that's not true for the obstacle case. We also created a heuristic solution to quickly have an estimate of the number of sensors that you can connect. And you can also trigger it at fractional nodes in the branch and bound exploration. So you can take a fractional solution and try to fix it using this heuristic. I'm not going to go into the details, but it's kind of a constructive heuristic where I have a location of a relay, and then I try to move it to some places that are within reach and where I have clusters of sensors. So I try to improve the connectivity by doing that. And we found that that was very effective when you do it at warm start, and it's kind of mixed results when we do it at fractional nodes in the branch bound. This is a sample of an instance. So I have two instances here, we just created a 200 by 200 grid, and then we have points there randomly generated. We have the left one is 100 sensors and 5 relays with these radius of communications, 15 for the sensor and 60 for the relay. And the one on the right is 200 sensors and 20 relays. And then it's stricter in terms of the communication ranges, is 10 and 40. So that's how an optimal solution would look like. So in that case, none of these was solved without the valid inequalities, and none of those was possibly solved with the conic formulation, second order cone formulation. So we represent solutions for FM. FM is the full model, branch and cut with the valid inequalities. We can solve a good deal of instances with that, and then things look better when I add the warm-up heuristic. And then when I have really tough instances, which are the ones on the right, with really small communication ranges, then I start seeing that the model starts, not being solved to optimality in 2 hours, and I have very large gaps. So we still have to fine tune that interaction between the warm start and the heuristic. Sometimes triggering the warm start and also the heuristic at fractional nodes works. Sometimes it doesn't. It's just a burden, and it's just a waste of time to go and try solutions, trigger the heuristic, but you don't improve anything. So we are on that. But we can solve a good deal of solutions of decent size with reasonable communication ranges. And this is how a solution for the obstacle problem looks like. I have these 3 shapes. Leftmost one is 100 sensors, 10 relays with those communication ranges. The middle one is also 110. And the rightmost one is 200 sensors, 15 relays with those shapes that I need to avoid. And these are the examples for these 2 landscapes, 2 square landscape and maze. For reasonable communication ranges, I can solve pretty much everything with our approach. When you have stricter communication ranges, then you start struggling. We allow this for 4 hours, and then sometimes you have really large gaps. So still, these ones are very tough. Large number of sensors, large number of relays, and also very small communication ranges. That makes the problem very difficult for both landscapes. This is what we're working on now, which is, okay, we have realized that some sensors will never connect to a relay. So you have already deployed sensors. They are already connected to other sensors nearby. So maybe the access point to that connected component is just some relays, some sensors, but not every sensor. So we have this concept of interior node. For instance, if you see this picture at the top right, the red ones, you just don't need them, because if you want to talk to that connected component, you just use a relay to talk to any of the nodes on the edge. So we have something now that just reduces the number of nodes or sensors by removing those sensors that you just don't need. And that's been really promising, because we could really prune that network and then get here and then solve the tough ones by just getting kind of in the ranges where we can solve, because you remove a bunch of sensors that you didn't need. So that's what we're working on, and that's all I wanted to show you today. I appreciate the invitation, and I appreciate the questions. I'm open for questions, and I think I made it in exactly half an hour.
Yes, that was perfect. So we do actually, even though it's a little past the half, we have time for 1 question.
Can I ask a question?
Sure. Yes, go ahead.
Instead of using the second order cone and the Euclidean distance, what about using square distances and Euclidean distance matrices and SDP?
Yeah, we could do. We didn't try that, but that's definitely possible. What we can do is, this approximation is flexible, and then we can use just subset of the U vectors and have a simpler shape and then live with that. So you can have a square instead of this polygon that I'm showing you. So that's definitely possible. We didn't try any SDP reformulation, but that's definitely worth exploring.
Ever consider the structure of any cliques? With
We
any
did.
cliques in the graph? Because if the cliques are known, then you can sort of recover things exactly.
We are using that for the network size reduction. So when we have really nice structures, cliques, or connected components that are already established, or they're already in the already deployed sensors, we can use that to explore the structure of that and then remove sensors that you don't need. So we are using that in the network reduction technique, and then the most we go with the structures already there are these constraints where we just create the independent set. But we don't exploit, as of now, we don't exploit the clique structure per se. We exploit structures to reduce the size and then for imposing these independent set constraints. But that's a good point as well.
Well, thank you for the questions, and thank you for everybody for the attention for Jorge. Let's thank Jorge one more time.
Thank you.
And he will be around for the breakout room afterwards if you would like to ask him more in a one-to-one or small group setting.